Section 3.2, Domain and Range. In Section 3.1, the last section, we did talk about domain and range. We mentioned them in the context of inputs and outputs. So if we have a function f, that function takes the elements of our domain and maps them to elements in our range, our outputs. Inputs to outputs. Now, we are going to, in this section, focus on listing or describing the set of numbers that are in our domain and range. Describe the set of inputs and outputs. And we often use interval notation when things are continuous. We'll use that as we need. So example 1, find the domain of the following function. All right. Well, in this case, our inputs is this list 2, 3, 4, 5, and 6. That is the list of all our inputs. That describes completely the inputs in this setup. Now the range is 10, 20, 30, 40. We wouldn't list those repeatedly, but we would list those for the range. Now, example 2, find the domain of the function f of x equals x squared minus 1. Now this is very similar to one of our parent or toolkit functions that we saw earlier. Now we want to describe the set of elements that we can use as inputs here. Now you can take any positive, negative, rational, you can take any number and square it. And you can always subtract 1. So our domain is all real numbers, which we will write as the interval from negative infinity to infinity. That covers every real number. No issues there. Example 3, find the domain of the function f of x equals x plus 1 divided by 2 minus x. We have a slight problem here because the only restriction that we could possibly have is not dividing by 0. Okay, so what value makes the denominator, 2 minus x, equal to 0? Well, x equals 2, which means in our domain, or our domain is going to exclude 2. In interval notation, the way we'll write that is negative infinity to, let's make that clearer, to 2, not including 2, and then we're going to also take the numbers from 2 to infinity. Okay. Negative infinity to 2, union 2 to infinity. Okay. There we go. Find the domain of the function f of x equals the square root of 7 minus x. The restriction we can have here is that we cannot take the square root of negative numbers without producing some complex values. So we need to make sure that 7 minus x is greater than or equal to 0. Now we dealt with that in chapter 1. Solving for x, we have that x must be less than or equal to 7. So for our domain, the way we'll write this is from negative infinity to 7. Now we're equal to 7, so we will include 7 as an endpoint. Next, we introduce the concept of set builder notation, and a little bit more about interval notation. Set builder notation is a method of specifying a set of elements that satisfy a certain condition. So you can see here we have the set x such that, that's our vertical bar, x such that, and then some statement about x. So we write some property there, and as long as that statement about x is true, then that is an element in our set. And then we have interval notation, which we've talked about again and again. We're going to describe the interval of values shown in this graph using inequality notation set builder notation and interval. Okay, kind of tie those together. So inequality notation would be we have x values that are between and including 1 and 3, or we have values that are greater than 5. All right, to write that in set builder notation, that would be very, very similar. That would be x such that, and then this statement we just made, that must be true. Okay, so there's our set builder notation. Now for the interval notation, which I personally prefer, interval notation would be we'd bracket 1 to 3, bracket because both of those are included, union, and then we start at 5 and we go towards positive infinity without including 5. So all three of those are equivalent. They are saying the same thing. Now I will often use interval notation as a preference, okay? But unless your homework specifically asks you for that, you can put it in any of these types of notation. Find the domain and range of this function whose graph is shown below. For our domain, okay, that is the x values, the input values that we can have. And if you notice, our inputs range from -3 to +1. So our input, our set of domains values is -3, not including -3, to 1, including 1. Our range, the set of output values that we can have, the lowest value that occurs on this is -4 as an output, all the way to our highest point of 0. Now you might say, hey, but it's an open circle over there at -3, 0, so how is that included? Well, that point that I actually just drew right here, 0, 0, the origin, that is solid. Okay, whenever there's not an open circle, it's assumed to be continuous in that fashion. So our range goes from -4 to 0, including both endpoints. Let's look at example 7. We've got an application here. Find the domain and range of this function whose graph is shown below. Now you could apply the vertical line test to see that this is a function. Now it's not one-to-one, just to tie that into talking before, it's not one-to-one. So the domain and range here are going to be given based on what we see on the graph. We'll have to estimate just a bit. It appears that the input values go from something like 1973, that's this area right here, all the way to what I'm going to presume is 2010. So in interval notation, that would be 1973 to 2010. My output values range from something right there to something a little over 2,000. And I'm going to go with the values that the book estimates those to be, which are 180 as a lower value up to 2010. All right, now the domain is our time, if you notice. Okay, time is our input, and here barrels is our output. So time and barrels. Now we're going to revisit our toolkit, or our parent functions. Each of these toolkit functions have a domain and range. The constant function Okay, the domain is negative infinity to infinity. There are no domain restrictions there. But the range is c, exactly the value it is, because it's not changing. It stays at that y value regardless of the input values. The linear parent function, domain and range, negative infinity to infinity. It continues to the left and the right and up and down. It increases for its whole domain. All right. Next, we've got the quadratic, or the absolute value. The absolute value function has a domain of negative infinity to infinity. Again, there are no restrictions there. However, the range is greater than or equal to 0. And we have the same domain and range actually for our quadratic. Okay, they're both above the x-axis as a parent function. Our cubic function acts very similarly to our linear parent function. Okay, that's an important fact for later. So it has the same domain and range. The reciprocal function, I referred to the asymptote that it has there previously. It approaches 0 from the going as it goes out to infinity to left and right, but it never gets there. So the range does not include 0. And the domain does not include 0 because we have a vertical asymptote right here. We have a very similar issue with our reciprocal squared. The difference is it will always be positive. Our range is always greater than 0. Okay, so we do not include 0 there, and it's always going to infinity. The domain does not include 0 because we have this horizontal asymptote, or vertical asymptote there as well. The square root function, if you notice, is always positive. You can only take the square root of positive things, and you can only get positive answers from that. We actually restrict it so that they are positive. Okay. Then we have the cube root function, which, as far as the end behavior goes, it acts similar to the cubic or the linear function, so domain and range are both all real numbers. All right, so each of these functions is going to be based on one of our toolkit functions. So looking at number 8, find the domain and range of f of x equals 2x cubed minus x. This is a cubic function. Okay, we can cube any number, positive or negative. We can then multiply it by 2 and subtract the number. So this actually has a domain and a range of all real numbers. Because the cubic function has that same domain and range, that's what happens there. Find the domain and range of f of x equals 2 over x plus 1. The domain is fairly easy, fairly straightforward, because we know that x cannot be negative 1. So there's that. So writing that interval notation, negative infinity to negative 1, union negative 1 to infinity. Now looking at our parent function, we see that the domain does not include whatever makes the denominator 0, but also the range there is always, it's not equal to 0. All right, so what I'm going to do is rearrange this. Y equals 2 over x plus 1 to make the range a little more obvious. If I solve this equation, I'm going to multiply by x plus 1 and divide by y. X plus 1 equals 2 divided by y. So x equals 2 divided by y minus 1. What y value can we not have? Our y value cannot be 0. We can't divide by 0 there. So negative infinity to 0, union 0 to positive infinity. We can always solve for x and then see what restrictions we have on y in that way. Sort of a handy tool when it comes to finding domain and range. All right, find the domain and range of f of x equals 2 times the square root of x plus 4. Well, just like previously with the square root function, the parent function, x plus 4 must be greater than or equal to 0, which means x must be greater than or equal to negative 4. So our domain begins at -4 and goes to positive infinity. Right, now our outputs, our ranges, that's going to be a little tougher. So let's go ahead and let's go ahead and do that. Let's go ahead and solve this. All right, y equals 2 square root of x plus 4. Okay, if I divide by 2, y over 2 equals the square root of x plus 4. Squaring both sides, we get y squared over 4 equals x plus 4, so that x equals y squared over 4 minus 4. Now that value is always going to be positive. In fact, the smallest y value, or the smallest x value we could have, is -4. And so this actually is just going to be greater than or equal to 0. Okay, so my domain is 0 to infinity. Okay. The last thing we have in this section is piecewise functions. A piecewise function is a function in which more than one formula is used to define the output over different pieces of the domain. So, example 11, a museum charges $5 per person for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for a group of 10 or more. Write a function relating the number of people n to the cost c. So the cost for n people to enter this museum or have a guided tour depends. Okay? If our value of people, if n is between 1 and 9, so we're going to go ahead and say this is between 1 and 10, not including 10. Okay? Between 1 and 10 people, it's $5 per person. So 5n. If it's over, if n is greater than or equal to 10, then the cost is a fixed $50. And that is a function that describes how that will work. All right. Example 12, cell phone company uses the function below to determine the cost C in dollars for G gigabytes of data transfer. Find the cost of 1.5 gigabytes of data and the cost of using 4 gigabytes of data. The cost of 1.5, well, 1.5 is between 0 and 2, so we are going to use this formula for that, in which case the cost is simply $25. Okay, that part of our function is a constant. To find the cost of 4 gigabytes of data, we'll have to use the second formula. 25 plus 10 times g minus 2, in this case 4 minus 2. If you notice, it is $10 for every gigabyte over 2 is how this was working. All right, 25 plus 10 times 2, so that would be 20. So this is $45. All right. $45 is our cost there. Example 13, and our last one for this section. Sketch the graph of a function based on this piecewise definition. So we have three segments of this. One is if x is less than or equal to 1. One segment is between 1 and 2, and then greater than 2. So let's go ahead and graph or sketch what each one of these looks like. X squared, okay, looks something like this, and I'll be a little more precise in a second. There's our first section. Now we only are concerned with that when we're less than or equal to 1. Then we've got the constant function 3. Just call that 3. And then we have f of x equals x, our identity function. Now that's if x is greater than or equal to 2. So what's going to happen here? We're going to first cut this one off at 1. And all that we need, let's box in the other side of that. We're going to use this function as long as we're less than or equal to 1. For the constant function 3 between 1 and 2, we're going to use this function. And greater than 2, we will use this function. Let's be a little more precise because we need to know what's happening at the junctures, okay, where they connect. So x squared, as long as we get to 1, well, at 1, the quadratic function is at a value of 1. Okay, so we have something happening like this. Okay, up until 1. Now that's less than or equal to 1, so that will be a solid point, a closed point. Now, between 1 and 2, we'll have the constant function 3. So there's 3. Between 1 and 2, we'll have that function. Now it's going to be an open circle there at 3 and a closed point at 2. And then the function x, if x is greater than 2. Now that is the identity function. So at 2, that function is 2. And at 3, it's 3, and it continues in that fashion. So that function looks something like that. Now these types of equations are actually pretty useful in real life or in application problems because life is messy. Life is messy. Okay, so that brings us to the end of this section. Be sure that you're familiar with the concepts of domain and range as inputs and outputs, and also determining when formulas are valid, because, as I said earlier, functions are a big part. They're a big thematic concept here, overarching theme, and so we need to be familiar with domain and range because they are an essential part of functions. That's our section.